This is our second session on SCUDEM student talks. These are three cadets from West Point, and they're going to talk to us about how to teach Fritz to catch. So I'll let you introduce yourselves and take it from there. Thank you.
Thank you. So first of all, thank you everyone for coming in to listen. We're very honored to be here presenting about our SCUDEM project. As Mr. Winkle said, we're going to be talking about the teaching Fritz to catch problem. And I'm Elizabeth Fetter.
I'm Alexander Seamark.
I'm Michael Hoefler. Let's see. A couple little technical difficult. Oh, there we go.
Okay, so sorry about that. Just the contents of what we're going to be presenting today. We're going to start off with a brief introduction of each of us. We're going to talk about why we chose to participate in the SCUDEM project, and then why we chose this Fritz problem specifically. Then we're going to dive in a little bit to the kind of the specifics of our models. But what we really want to focus on is there are three iterations of models and why they became increasingly complex, and sort of why they needed to become more complex, as in what each successive layer of model did in a better way than the one before, if that makes sense. So kind of like the limitations of the previous model and then the advantages of that new model and why we chose to advance to that newer model. And then we're going to talk about kind of the conclusions that we got from SCUDEM specifically, and then where we could potentially go next in terms of math. And then as well, we're going to talk about some difficulties we encountered actually trying to kind of solve the problem and create these models. So for the introductions, as I said, I'm Elizabeth Fetter. I'm a freshman at West Point. I'm going to be double majoring in international history and Mandarin, and that's a photo of me.
I'm Michael. I'm a freshman here at West Point. I'm planning on studying electrical engineering.
I'm Alexander Seamark. I'm also freshman at West Point, and I'm planning on majoring in civil engineering. So originally we were in class with our teacher, Major Mussman, and we were having lots of fun learning about differential equations. And then he brought up this competition named SCUDEM, where we could apply some of our knowledge about differential equations to real life. And we thought that'd be really interesting, because what's the point of learning anything if you can't like apply it to the real world and solve some problems to better humanity and help the world, I guess. So that's sort of how we heard about SCUDEM and why we decided to participate in SCUDEM.
So we sort of, why did we pick the problem that we picked? Well, we scanned the problem selection, and the Fritz problem looked particularly interesting to us, since it would not only involve differential equations, but we would also get to work with some physics and dogs at the same time, which just, it looked like the most interesting problem on the list. So we sort of started by applying our knowledge from the differential equations class to the problem and sort of creating a basic model. And then once we got through that, we sort of looked into some existing research on how humans catch things, which we sort of applied to the Fritz problem.
So some assumptions that we had to outline just as a basis in approaching this problem and kind of break it down and simplify it, as Michael was saying, is that there aren't any obstacles for the dog running into, that the dog can sort of run fast enough to catch the treat, and that the dog's not going to jump to catch the treat. So this actually varies a little bit in what we saw in the video that was provided in the SCUDEM project outline. In the video, it was the food was thrown in an arc at the dog, and the dog would sort of jump to catch the treat. And the way that we were modeling it is sort of more like a person catching a baseball, but analogously a dog catching like some sort of treat-like object, but from further away, and the dog's going to be running at that treat. And then, so again, from there, we need to know, or we had to assume that there's not going to be any air resistance or any other outside forces. And so these are the variables that we used from there.
Okay, so as Fetter was saying, we're working in 3D. These are our parametric equations for the motion of the treat. These pretty much arise just from physics, like projectile motion is where the Z component comes from, and the X component. And to simplify things, we decided to keep the Y component constant for our first rendition of the model. So that's basically just the position of the treat with respect to time. And then moving into our basic model, we started by considering like a really simple linear system of differential equations where the rate of change of the x component of the dog is proportional to some combination of the x and the z component of the treat. And similarly, the rate of change of the y component of where the dog is proportional to a combination of the y and z position of the treat. So this is a pretty basic model. We're only considering the dog on the plane, and the treat is actually moving in 3D space. And the dog is just gonna move with respect to xd of t and yd of t is going to be the position of the dog at time t. So basically, if we just separate and integrate, like we learned sort of in the beginning of Major Mussman's class, we can come up with a solution, as you can see here, to that differential equation. And then Fetter's going to talk about some advantages and disadvantages of this really simple solution that we came up with.
Right. So as I said initially, in each of our 3 models, they had advantages and disadvantages. And a really big disadvantage to this model is that it's very basic and that it relies on these A, B, C, D constants. And so if we plug in accurate numbers for these A, B, C, D constants, then we can get a model that really accurately represents the dog catching a treat in projectile motion. But the trouble is we can't really get those constants very easily, especially A, from that video that we saw. It doesn't exactly reflect what we're modeling with the dog kind of catching a treat, more of an arc. It's sort of just instead of dog jumping and catching a treat right there. And then also, even if we looked at, like hours or like hours and hours of data of dogs catching baseballs or dogs catching treats, it'd be pretty hard to determine these constants like through looking at that. And so this is basically just acting as a starting point, as sort of a baseline for what we then went into with more research that, hey, so this is our baseline. This is sort of like a very basic model of the dog is going to move based on where the treat is. And then where can we go from there? And sort of our next steps, we looked online at other research, at what other physicists had done, what other mathematicians had done to kind of base our more advanced models. And my partners are going to talk about that next.
All right, so we weren't very happy with the last model because it relied on a lot of assumptions. So we weren't quite sure where to start, but we ended up looking at the American Journal on Physics and trying to see if anyone had done something sort of similar to this problem. And while we were looking through the journal, we ran into this model made by Chapman in 1968 called the optical acceleration cancellation model. And it basically assumes that it deals with baseballs, but we're going to talk about it as for Fritz in the case of a dog. So it basically assumes that the dog's going to run in a path where the toy will maintain constant optical velocity or the treat. And what that means is that the treat or the ball is coming at the dog, and the dog is going to move forward or move backwards so that the treat appears to have a constant optical velocity in the eyes of the dog. So it appears to be moving at the same rate, because scientists found that it's much harder for humans and dogs to catch something when it appears to be accelerating and decelerating. And so how we started to really break down this model and to understand what was happening was we made a diagram that you can see in the bottom left corner, and then we defined the key variables to lead us to the equation that was given to us by the model. And we found that it was really important to start breaking it down to like the separate parts and each like truly understanding each variable so that we can understand how they got to this equation. And there's also one more advantage that this model has, along with being that increases its how realistic it is that I'm not sure if you can see it, but there's T minus I forget what the symbol is called, but there's a delay included in there.
Tau, maybe?
Yeah,
I think?
tau.
T minus
T
tau.
minus
yeah.
tau, and that
So many Greek letters in math, and it all
that
gets.
counts for the delay that the dog has in initially recognizing the ball that's being thrown at it. So like when the ball is thrown, the dog doesn't immediately recognize the ball is thrown, which adds for another. So that model, this model accounts for that and adds for more realism.
So I think like kind of adding on to what Seamark just said, a really neat part about this model is that it's starting to really go into the physiology of animals and humans. So like our first model was basically just like these math assumptions that we made of like, hey, it's going to vary based on this and this. And this one, as he just mentioned, it actually accounts for that delay time where it's like, I see an object, but I don't recognize that it's moving yet. And then, oh, once I recognize, now I'm going to start moving. Like, it's not going to start moving immediately. So I think this model and the next one too, really, the reason why they're more complex and kind of like the next elevation is that they really start to account for that, the physiological nature of humans and animals and whatever it is that we're trying to model in a way that that first most basic model really didn't.
So this just goes farther, more into depth than what Chapman was doing in his research. So on the right here is where we really focused in on, and this is the tangent of elevation angle. And this just shows how if that angle increases at a constant rate or a linear rate, it will the ball will be caught. But if it increases at like a non-linear rate, the ball doesn't end up being caught. It goes into one of other many scenarios. Yeah. And then the elevation angle of the tree as seen by the dog is standing from distance S from the tree, where the tree come down at a distance R from the origin. And after several algebraic manipulations of the equation that we showed a couple slides ago, you find out that it's a constant times tangent of phi is equal to a constant times t. And this shows how it's important that for the dog to be able to catch it, that they have to maintain that constant optical velocity.
Yep. So sort of going off Seamark's model, we looked into some of the models that had been proposed afterwards, and a couple criticisms of the optical acceleration cancellation model that he was talking about is that some physicists were saying that humans can't actually detect small changes in acceleration well enough to actually move with respect to this model that Seamark was talking about. So one that was proposed later is called the linear optical trajectory or LOT model. So that's going to be the one that I'm talking about. So what you can see here is we're considering like a simplified case in 2 dimensions where the red arc here is the trajectory of the treat, and then these black points that are sitting on the x-axis are the dog running towards the treat. And what the LOT model assumes is that basically the angle from the dog to the treat is going to remain constant. So what you're going to end up with are actually a bunch of similar triangles here whenever you draw those angles that decrease in size as the dog gets closer and closer to catching the treat. And we call that angle right there on from the x-axis to the treat, we call that angle gamma. And we're going to talk about that a little bit more on the next slide. So if we look at the triangle and we do a little bit of trig, we can take tangent of gamma, and that'll give us the ratio of the y of t, the y component of the treat, over the x of t minus the x position of the dog of t. That denominator is basically just the length of that triangle from the last slide. It's the difference between the x position of the dog and the x position of the treat. So that's what happens whenever we take tangent of that angle. And whenever we do a little bit of manipulation on that to solve for the x position of the dog, we get a really nice model for xd of t, the position of the dog with respect to time. And that's what's in this blue box on the bottom.
And just bouncing off of that to compare it to our old models, whereas that first model, like I said, that kind of the issues with that is that it has so many of those constants that we just are not necessarily arbitrarily determining, but kind of just like guesses. What's really nice about this model is that it doesn't really have those constants. And again, it's more based on kind of like the actual real world scenario of that dog creating those similar triangles to eventually catch the treat.
Yeah, and we were reading through some of the literature, and they've tested like both of these models on baseball players, and they found that this one was a little bit closer to the actual data that they looked at, this lot model. So that was sort of interesting. And yeah, as Elizabeth was saying, if you had like a data set, it really would take a lot less data to be able to employ this model than it would to use our first model where we had all those constants. And this is just another figure. The author actually introduced a third dimension with the lot model to further describe like baseball happening, in 3D space. And the model gets a lot more complicated from there. I won't go into the details, but you can see that instead of one angle, you end up with two angles. You have alpha and beta, and it gets into a lot of trigonometry to basically solve for the 2D position of the baseball player over time as they run on the field to catch that ball that's in the air.
Okay, so these are kind of some of the conclusions. And one thing I was thinking about is sort of in the scientists in the literature that we were reading, that they looked at data, and I was wondering how much of this is like subconscious in the minds of either the humans catching the ball or the dog catching the treat. Like, I don't think a baseball player going to catch a ball is thinking, I need to keep this ball constant and create, similar triangles. Maybe that's kind of like a Sherlock Holmes type sci-fi thing happening there. But I think most baseball players just kind of intuitively go catch the ball, or same with dogs, intuitively go catch the treat. And yet we decided that Fritz isn't necessarily bad at catching. He just needs maybe a little bit more practice, and it could get better. And maybe he was born with maybe a little bit more limited neurological capacity to make those intuitive judgments about where the treat is in relation to his position, in terms of those kind of similar triangles or optical velocity. But he's not necessarily, maybe he's starting out at like a lower baseline, but if he does a little bit more practice in catching the treat, then he's going to be able to get to that same level. And this is some other questions asked on the SCUDEM, that the owner could make it harder for Fritz to catch the treat and thus make a little bit more money making these funny viral videos if it adds like a little bit of spin to the treat, or uses even more like oblong shaped. Like I think in one it was catching like a hot dog, and like if a hot dog's spinning over and over, it's going to be easier to catch the hot dog if it's like in this direction as opposed to this direction. So kind of like the owner of Fritz could play around with that if he wants to make a little bit more money making these viral YouTube videos. Okay, so here were some of the complications or issues or challenges that we ran into using this model.
Yeah, so whenever we were doing the research on this, what we found is that a lot of the existing models for catching really didn't involve differential equations. So you'll notice that those last two models that we talked about, they use a lot of trigonometry and quite a lot of like algebra to manipulate those equations to solve for the dog's position, but they really didn't use many differential equations, which was a bit of a challenge. Also, it's not always clear like which approach is the best one, especially whenever you're looking through all of those research papers and white papers. Like sometimes it's hard to tell which ones are better supported by data, and which one is going to be the best to go with.
On that note too, kind of a big basis of our latter two models were that they were off of data and work that other scientists had, or physicists, mathematicians had done, and they didn't really involve dogs and treats. So that was sort of a complication that we had to adapt the parameters of information that we'd found online that were like similar situations but not exactly the same, and then sort of change them to fit what we wanted, and then as well as adding our own kind of our own twists to it, or our own uniqueness to the models. And then the third bullet point is that, or the third and fourth one sort of again touches on those kind of the open-endedness, especially with that first model of like we're using a lot of constants here and sort of the data is unclear. And even as I mentioned previously, with Fritz catching a treat, it was just like the small throw and Fritz was jumping to catch it. And the way we modeled it was a lot more in parallel to a dog catching or a person catching a baseball, because that was the data that we were working off of.
Yep, so some directions that we could possibly go in the future. Some of these models, we could really look at them fully in 3D instead of like eliminating one of the dimensions to make it a little bit simpler. It would obviously be a bit more complicated, probably involve a lot more algebra and trig, but that's a future direction that we could look into. We could also consider if maybe if Fritz was on a leash or if Fritz was encountering some kind of resistance going for the treat.
Using some kind of Dirac delta or step equation. I know we actually learned about those two in class just after we finished making the model, and we were talking about it like, oh, it'd be so fun to add like the 1 instant of force, like when he breaks the leash, or kind of like unit step functions of the leash gets increasingly more, kind of like fun playing around with that, or air resistance or treat shape, kind of as we mentioned earlier. We can play around with those to, it's I think pretty easy to make this very quickly more and more of a complicated problem.
Mhm.
So that's kind of it for our presentation. Thank you all for taking the time to listen, and yeah.
Well, thank you very much. Are there any, yeah, we all want to thank them for sure. And are there any questions or comments from the audience? Just speak up. We have a small enough group.
Hello, I'll start off. So thank you for the lovely talk. It was really enjoyable. I love dogs, and baseball's okay. Okay, first is like a super loaded question, all right? But I want to hear your thoughts on it, and it's super open-ended, so don't feel like you have to get it right or wrong. Earlier you were commenting on your linear models, I think. Not linear, but your models at the beginning were very simple, but they introduced these parameters you don't know. And then later on, when you got to the 3D model, that was like really challenging to solve, obviously. What are your thoughts on balancing realism, like modeling the real world, and solvability? Do you guys have thoughts on this? Like, this is a loaded question, all right?
No, I actually that's interesting. And I think I think we're all taking econ right now, which is somewhat tangential, but I think econ kind of deals with the same issue where you oversimplify these models to make them sort of more palpable and solvable, but then it's like, wait a second, that doesn't actually reflect what's happening. So I think the simple models can be really effective and useful in terms of understanding a concept. So kind of what we did, we used this really simple model at the beginning to build a foundation and a base for like, hey, this is sort of just like as a baseline what's happening. And then once you have that understanding and that kind of basic knowledge, then you go and either look at more real world data kind of in that research that we looked at, or you kind of, you make an increase in the complex. So kind of in my parallel for econ, you start with like the most basic trade of like guns and butter for like whatever a country's production, and then you like increase in the add like world trade, you add taxes, you add price caps, kind of things that make it more complicated but more similar to the real world, if that answers it.
Yeah, it's a really hard question. I'll just give like I do want to let you guys chat, but I'll give my thoughts on the way to do this. It actually has to do with your last slide. You're I think 19 or 18. It was a loaded question, all right. I think ultimately whether you go for realism or solvability depends on your goals, right? I'd say the mathematician's goal is to make, in my opinion, mathematicians make the problem easy enough to solve. Whereas if you're doing something like business, you don't care about solving it, you care about securing the next contract. So then you just need to make the figures pretty enough that they'll secure. Who cares if it can't be solved, as long as you secure the next contract. So since this is a math journal, I'd say math, in my opinion, is about making the problem easy enough to solve exactly, or at least with the computer. But again, if you want real world, like if you want to answer baseball statistics, maybe you don't need solvability. You just need something that can make predictions. But anyways, thank you for the...
No, thank you for your perspective.
Thank you.
We appreciate that.
Good answer.
I've looked at all these videos that all these teams submitted and had wonderful days of doing it. And I noted you pointed out delays. So you introduced the notion of a delay, which is not in standard differential equation courses. And that came about, no doubt, because of your reading, I guess. Yeah, and also I began to think about frisbees. You know, they have these tournaments where, and of course, a frisbee lingers, and that's and then your analogy to baseball. There are lots of papers written on how outfielders, you know, what they do. I mean, you know, from the crack of the bat, they seem to move, and the question is. And then you'll hear the announcer say, oops, he came in and he should have gone out, you know, and this kind of stuff. So I like that analogy. And lastly, I wanted to suggest to all the faculty who are listening that what we need to do is you need to go over to your history department and your Mandarin department and recruit people to take your differential equations. It's well known that engineering faculty are always sending your students, but Elizabeth presents a unique perspective. I want to thank you very much, and I have to go to introduce our next speaker on the wiki models, but I wish you well in your studies. I thank you for your service, and keep on keeping on, okay?
Thank you very much, sir.
Thank you.
Thank you. Take care.